Hello, everybody. This is Erik Novak from Ph.D. Technology, and welcome you to our webinar this afternoon, Factory Floor Surface Measurements to Increase Yield and Profits. Please feel free at any time during the presentation to type questions into the questions box. And at the end, we'll also open it up for further questions. And if you have measurement requests, we'll be able to handle those as well. I'm joined today by Kramer Lindell, one of our applications specialists on the Inspect product line, as well as by Gwendol Girard and Alessandro Baratti, who are our local representatives in France and Italy, respectively. So with that, I'm going to start with a few presentation slides to introduce the topic at hand and what we'll be talking about, and then we're going to get into live surface measurements that will hopefully illustrate some of the points in a lot better fashion. So surface measurements can encompass many different things. Hold on. Surface measurement can encompass many different things, including roughness, waviness, shape, microgeometries, and defects. And each of those typically will have different measurement tools that will address the needs of that type of geometry. And today we're going to be talking mostly about microgeometries such as radii, chamfers, blend radius, things like that, as well as defects, so pitting, scratches, nicks, dents, and other things that can affect the quality of both new components as well as used components, say in a maintenance setting. And microscale defects have a significant effect on components. They'll, of course, affect performance in terms of pitting, porosity, scratches, all can affect efficiency. Nicks and dents can cause leaks in critical sealing surfaces. Burrs can, of course, cause damage to other parts. Edge break can affect fluid flow. There's also effects on lifetime of parts. So having defects can lead to excessive wear. They can initiate corrosion, and structural integrity can be compromised if there are voids in additive manufacturing processes or even in certain casting operations. And chamfers and edge radii are critical to prevent cracking, particularly in high stress surfaces. And then, not to be discounted, perception is, of course, a very important part of the quality experience for any company and customer, right? The human eye is excellent at seeing very small flaws, but terrible at estimating their size. And customers will typically reject parts they suspect as being bad, particularly if there's no quantitative measurement to prove otherwise. Metrology investments can save time and significant money. According to Quality Digest, poor quality control costs an average of $2 million a year over the 100 companies they surveyed in the manufacturing space. And the US National Institute of Standards and Technologies performed 16 different economic studies since the year 2000, and they showed the average benefit of investing in metrology is almost 50 to 1. So if you look on the right, $1 of prevention really can save, more than $100 in failure costs. It's very important to get metrology right, and many people think of it as not adding value to an operation, but absolutely it's critical to process control and profitability. Good metrology systems rapidly pay for themselves, and mainly by reducing two things. One is internal failure costs, and these are things like waste, scrap, rework, the time it takes to reinspect parts, failure analysis, Some parts get binned and downgraded if they have flaws. And maybe most importantly, reducing part shortages. So particularly, say in aviation maintenance, part shortages are the #1 driver of turnaround time. So if you can save more parts, you can reduce turnaround time and again improve satisfaction as well as profitability. But there's also external failure costs, and these are outward looking costs. They include things like repair and service costs, warranty, handling customer complaints and returns, travel that it might take to handle a downed component, post-warranty costs that are incurred, and then not to be discounted, things like customer dissatisfaction and perception. If they're continually getting parts that they feel are flawed and there's no quality controls on them, they're going to move on to a different supplier. And measurement capability, really is not all about the instrumentation. There's three critical things that must be balanced. One is, of course, the instrument itself must have sufficient resolution, must have the capability of doing the measurement. But then the operator comes in to play as well. So you want the instrument to be simple. It's got to be robust. It has to, be easy to use for the operator. Small time to results. And then lastly, the environment. Measuring only in a metrology lab is very undesirable. So you have to think about where the product is going to go in order to move onward. And traditional shop floor inspection methods really are insufficient for today's production processes. But surprisingly, many places still use visual inspection and fingernails and scribe gauges, and look at surface contact in order to estimate depths. These are very operator dependent and non-gauge capable. Additionally, there's things like replication combined with surface profilers. These can lead to high material costs. It's a very time-consuming method, typically 30 plus minutes before you get a result. And again, it's operator and material dependent. Did the replication material really get to the bottom of the scratch? Was the operator actually able to estimate the exact deepest point of the scratch or pit for cross-sectioning? And what happens is, particularly in high cost of failure environments like aviation and automotive, that when in doubt, people will just reject or rework parts. That becomes quite expensive. So now we're going to do a little test. We're not actually going to poll you, but this is just for you to think about. These are 6 different images, bright field images of defects on an aviation component. And when you look at that, think, and these are obviously at high magnification. You can see a lot of detail. Think about which of these pits is the shallowest and see if you can guess. And you might not have guessed that it's the one in the lower left. It's actually one of the larger pits. These are all at the same magnification, but it's a very shallow pit. And one of the deepest pits is actually the smallest one in the upper center. So again, visual inspection just is insufficient at estimating things like depths, and even widths and things are difficult. You might move on to some handheld 2D or 3D, laser scanners or stereoscopes. But the problem there for microscale defects is they simply lack sufficient resolution. Therefore, they're non-gauge capable. The 2D systems just won't capture the full defect, and so it's unclear whether you've measured the deepest point. And they can be very sensitive to material finish. The 3D scanners, of course, will see the entire defect, but the resolution is typically even more limited. So they're very portable, convenient devices, but not capable of measuring microscale geometries and defects. So here's an example of that, where just moving where you're looking across a defect by several microns can actually cause almost a 30% variation in what you would think of as the pit depth. So if you just had a single trace, it becomes very difficult to estimate. If you have a 3D technique, though, and look at the entire pit, as you see on the right, in the light blue, you can get a very accurate depth measurement instantaneously and not worry about operator error. Lab-based metrology typically has plenty of resolution, but it becomes impractical for most shop environments. The systems are very costly, they're limited to small parts, the operator typically needs a lot of training, and because metrology labs are typically very busy, it can be hours to days before a measurement is completed and results are known. Then contact-based profilers, stylus profilers, again, they're 2D systems that can sometimes do 3D very slowly, but they're again expensive, again limited to small parts, and measurements can take several minutes. So you have enough resolution with these systems, but it's just not practical for cost-effective shop floor inspection. 4D technology uses a technique called polarized structured light, and that's designed to allow vibration immune handheld metrology. So structured light uses the bending of projected lines in order to estimate surface shape. And typically you would need 2 or 3 different stripe patterns or different colors to come up with a 3D picture like you see in the upper right. But we actually use custom cameras with small polarizers in front of each pixel that actually allow us to get the 3D information in a single camera frame. That means you can be holding the device, you don't need vibration isolation, and you get a full 3D image very quickly. And then the goal is make shop floor 3D measurement as easy as taking a picture. So here we have some different examples where you have a tactile focus aid that gets you to the right distance. You merely bring the device up to a part on the shop floor, hit an onboard trigger, take measurements. Kramer will be showing you a lot more of that. Just to go over some basic specifications, this particular product comes in 2 models, one with an 8mm by 8mm field of view, one with about twice the field of view. Vertical ranges can be as high as 9mm, and resolution is somewhere between 3 and 8 micrometers, depending on the model. So this is sufficient for almost all defect, edge break, radius callouts that you're going to see on typical machine parts. Also, high lateral sampling allows you to measure very narrow things. I'm not going to go a lot of detail here. You can read this on your own, and Kramer's going to show a variety of results. But the upshot of an optical technique is it is typically capable of measuring most any material and a whole variety of part types. And once you have that 3D information, you can do all sorts of different types of measurements, rivet depths and cooling hole geometries, laser marks, blend radius, rivet protrusion, all are capable with a 3D result. And the upshot of that is significant cost savings for most of the users of such tools. So these are real live examples from various people in aviation, automotive, and other industries, where they've been able to reduce rework rates by more than 30% by measuring the corrosion and wear properly and actually being able to have confidence up to the specification line. They've been able to reduce measurement time, sometimes from days to hours, by having rapid onboard results. Yields go up, labor goes down, and overall, profits again will rise. We'll get into and let Kramer talk about the feature analyses, but again, automated analysis of the surface provides operator independent results. Such systems are typically integratable with robotic automation, and Kramer will show you that, and with third-party software, so you don't have to be tied just to our instrument, but you can use robots. You can use your own automation and treat it as a measurement tool. And really, the goal is, to meet the various requirements of a typical production operation or maintenance operation. The keys are rapid results that are accurate, high resolution, can measure any component you throw at it, and have intuitive, easy software so that the operator can get on with his day and not spend time on the inspection process and not wonder whether or not he's really confident in signing off on parts. So with that, I'm going to turn it over to Kramer to actually show you some various results, and we'll come back later for questions. Thank you.
All right, so I'll go ahead and share my screen here, and I'll let you guys see my setup. And throw that my way. All right. So here is my setup. I have the 40 inspec here in the microscope stand. So I have it in a desktop mode here. I'll take it out in the handheld mode. You can see here I have a blue LED coming out of here at an angle through some lenses up here, reflecting off of a surface. You can see, and that's just the blue LED. It's eye safe. It reflects off of a surface, goes back to a camera right in here. Anything this blue LED reflects off of, you can get a 3D surface map of that surface. So I can take a measurement of anything on my table here, and if you have any requests on what I can measure, please feel free to jump in, and we can take some measurements for you. So to start, I'll go ahead and take a measurement on some dot marks here, just to show you what that looks like. To take a measurement, I have this in handheld mode right now, which is uses this focus aid. So this is a focus standoff that helps me get to the right focal point. Allows me to put this inspect down anywhere, take a measurement by clicking this button right here. So I can just put this inspect down on my surface, my area of interest. When I want to take a measurement, I can click this button and I'll get a 3D surface map of whatever this LED is reflecting off of. So I'll go ahead and start taking some measurements on this area. I'll go to my 4D software here. So this is the live video right here. You can see this is what the camera is looking at right now. So you can see I'm looking at some dot marks here. And when I'm out of focus, I am gray. I'm blurry. And when I'm in focus, get that in focus there, I'm green. I'm sharp and crisp. When it's green, we say green means go. And we're gonna take a measurement. And you can see on this left side, it's adjusting the brightness. So we have an auto brightness feature. As I adjust the brightness or the amount of light going into the camera, the brightness automatically adjusts as needed, just the exposure time and the gain. So I can take a measurement when my screen is green. I'll take that measurement by clicking that button I was showing you. This is what the measurement looks like right here. I'll go ahead and close some of these. So I'll go back to my measurement. So we have a feature analysis page that allows you to pick out any pits. Yes, sir.
Maybe start with the three-dimensional result just so they can.
Yeah, so I'll show you guys, there's a few different ways to view a measurement. We can look at it in this feature analysis mode. We can look at it in this 3D view of it. This is what the three-dimensional surface map looks like of this image I took. And you can see this is a good way to visualize what you took a measurement of. We could take some other measurements of different surfaces. Really helps you understand what the shape of the part looks like. And so each of these pits can be picked out individually if they're deeper than 10 microns here. And this is adjustable. I can change this to say 25 microns if I wanted to. and everything deeper than 25 microns is going to be flagged as a feature. So each one of these pits is being flagged as a feature, and it's a height, area, volume, length, width. Everything you want to know about this specific feature is plotted out right here. If I'll click on this one, it tells you where it is on this feature analysis map. And each one of these is individually and simultaneously analyzed for you. So you don't have to analyze each one of these individually. It does all the work for you. And it's very quick. One click of the button gets you all this information, all these data. And I can go ahead and take, we had some requests for a measurement of a scratch. I'll go ahead and take a measurement of a scratch here. We have some deep scratches here. I'll take a measurement of one of those, and just the same way, I will put the instrument up to the scratch, like so. And when I'm ready, I will go ahead and click this button and take that measurement. Anything this blue light reflects off of, I will get a surface map and be able to analyze the defects. So this has just a variety of scratches on it. It's a little bright that I can analyze. And the fact that this is so shiny and bright doesn't affect us too much. It doesn't affect us at all. Our auto brightness can adjust for that, and we can take measurements on bright surfaces just fine. Go back to my software, go back to my live video, and I'll go ahead and take a measurement on this scratch right here. So my auto brightness, you can see when it's red, I'll go off again when it's red. Those pixels are overexposed, but the auto brightness quickly, instantaneously drops the exposure time down. Let's take a measurement of this scratch. I'll adjust a more appropriate depth. So you can see right here, this scratch, I'll show you what I'm looking at. This scratch is being flagged as a feature. And right now I'm using a centroid view for the feature analysis. So this whole thing is, all these pixels are deeper than 10 microns, and they're all being flagged as a feature. So the centroid cursor right here is pointing to the point on this feature that is a mean of all these points on this feature. So, and if we want to know where the maximum depth along this scratch is, I can just click this max depth, and it tells me this is the deepest point about right here on this scratch. So there's a couple ways to place these cursors. This maximum depth is right there, and you can see that's about 44 microns deep at this point right here. So it does all the work for you. You don't have to guess with a stylus or some other form of measurement where exactly this deepest point is. You can measure the whole thing at once with your 3D data, and it tells you exactly where the deepest point is.
So this might be a good feature to show them the traces analysis on,
Yeah,
since that would
exactly.
additional way of measuring this would be with a 2D stylus.
Exactly. So this is the feature analysis page. I showed you guys the 3D view of it. Here's a good look at it. Helps you get a good understanding of the part itself. And now I can look at the traces view. So it's going to give me some two cursors here by default. This is just an X and a Y cursor, so I could have a X down here and a Y right here. I'll go ahead and just focus on my X cursor only, and I can move up and down here. And if I want to be perpendicular to this, I can draw my own custom cursors. So there's a few different options there. I can draw a cursor here, and I can up this width. So this width is the amount of pixels wide this cursor is. I like to keep it at 10, just so it averages over 10 pixels. And I can highlight a certain area where the scratch is, if I want to know how deep this gets. So I think the scratch is about right there. And then my peak to valley is the highest to the lowest point. Difference between the highest and the lowest point is being displayed right here. We also have the width of the scratch being shown right here at 364 microns. And you also have a delta Z if you wanted to do a left side of the cursor to the right side of the cursor difference. So this right here would be about 26 microns, almost 27. But if I want to get the width of the scratch and the depth of it at the same time, I can highlight the entire scratch, look at the PV, look at the this value right here, and I can also drag this cursor around and look to see where the deepest point could be. We know it's about right here, and we can check that out, see how deep this is around here. So it's a pretty useful tool, being able to move this around. You can see we can get up to 40 there, 41 microns. So it's a pretty useful tool, and you can see if you're using a stylus, you wouldn't exactly know where to guess. You'd take a lot of measurements to find out that this is the deepest point. With this 3D data, you measure it all at the same time, and this feature analysis picks it out automatically for you and points it out for you right there in less than a second. So it's a pretty powerful tool using this feature analysis. So those are a few different ways to view the measurements. We can go on to some different shapes of parts. I can plot some different parts here. So put that back over here. And I can look at a curved blade right here. So you can see I have a defect circled right there on this curved blade right there. So I can go ahead and take a measurement on this defect right there with the inspec.
And
Take this back
Kramer,
out.
have you gone
Yes,
over
sir.
the geometry of the device yet? How the light comes out and
Yeah. So this again, this light is coming down from LED through some lenses, coming at an angle down through here, kind of just along this parallel to this nose piece right here, down out, reflects off a surface and back to a camera right here. So it's coming at a little bit of an angle, reflects off a surface and back to this camera. That's the path of the light.
and how safe is the light coming out?
Yeah, it's just an LED, so it's eye safe, and if you wanted to, you could stare into it, but I wouldn't recommend it. But you could if you wanted to. But it's just an LED, so it's eye safe.
So it's like looking into a LED flashlight essentially.
Yeah, it's exactly the same thing. It's an LED. That's all it is. It's just polarized and structured in a way that allows us to take 3D measurements with it.
All right, thanks.
So I take a measurement on this curved surface with this defect. I can do the same thing I've been doing. Put this focus aid down, get this LED reflecting off my area of interest, and then clicking a button to take the measurement. And because I have my focus aid already set at the right focal distance, it's really just placing it down and clicking the button. I'll go back to my 4D software here, back to my live video. I'll get that in focus right there. It's green. And all I have to do is get my area of interest in focus, like so. And I'll go back to my measurements. So look at my 3D view of the measurements. So you get an idea of the curvature of the part there. You can see this curvature. And this on the contour map, which is one we haven't looked at yet, this is a false color height map where red is high, blue is low. And you can see that in the 3D data right here. You can see that curvature. So when I put this into feature analysis, it's going to think that this entire curvature of the part is a feature itself. So to remove that shape in order to use this feature analysis, we can put a variable shape removal on and recalculate this surface. So I can go back to my 3D view, recalculate the surface with our variable shape removal on, press recalculate, and you can see that this will flatten this measurement out. So let that recalculate right here. And we'll see the difference between this curvature and then this right here will be nice and flat. and this defect really stands out now. So you can see this is basically flat. Here's our defect, and I can put this into feature analysis. I'll let this do a more appropriate pit depth right there. And here we go. So here's our defect. Its depth is 318 microns. It's a nice big pit, nice impact, and that is a nice easy way to quantify this pit depth on a curved surface using this variable shape removal, which allows us to remove the shape. You can see the difference between this view and this shape removal right here when we were just removing tilt, which is the tilt of the inspect relative to the part itself. And again, this is the variable shape removal. So that's a powerful tool. It allows you to use this feature analysis on curved surfaces. All right, we can move on to some blade edge measurements.
Kramer, before you do that, do you want to explain to folks how the zero level is set and how you can custom set it if you need to?
Yeah, I think I'll grab a good part for that. Go back to my desktop here. So I'll grab a part with some different heights on it, and this will be good. This has some different dimples on it that I can set a reference to. So I can set to my zero level, and this will be more apparent what this looks like on a 3D surface view. So I'll go and take a measurement.
And that's now black rubber, right, as your surface you're measuring?
This is black rubber. So we can measure black rubber. We can measure the shiny material, the shiny metal. This is shiny too on it, but this is right here. But this black rubber is dark, and our auto brightness adjusts for that automatically, so you don't have to. But I'll take a measurement on this the same way I always do, placing this inspect down, the focus aid, and it's clicking that button. So I'll go ahead and go back to my live video. I'm in focus here, and I'll just take a measurements right there. Go back to my measurement here. So you can see I removed no shape at all. That's what I had selected here. And I'm in my contour map. It's probably the best way to look at this. My blue is low, my red is high because my inspect was slightly tilted when I took the measurement. Just by the way I had it placed, but I can set a mask on here. So I'll go ahead and go to my reference mask. So if I want this to be my zero level, I can go ahead and crop this area, rotate it to fit this, and set that region to be my reference mask. So everything can be measured from this area. I'll go ahead and draw another one here on this side. So everything will be measured from the mean of these two. All right. All right. So recalculate that with those masks on. Try to flatten these out. So here you can see the difference between these. I was blue here, red here, and now I've flattened this out, and I've set this point to 0. So in the traces view, I can adjust my cursor I made. You can see that this is 0 on the trace. It's at the 0 level. It's at the 0 level as well. Or before, this is at 0. This is way below 0. But now I know I can set this to 0 based on these masks. I made a reference mask, put them here at my points that I wanted to measure from. So now all these depths will be measured from these points that I have set. So I can set this into feature analysis now, and these these pits, or I guess these troughs, I guess, right here, will be measured from these points that I set. So I can have total control of what each of these values will be measured from. So this is a nice tool to be able to do that with. So that's basically how using a reference will work. And
Hey,
some
Kramer?
more masks. Yeah, go ahead.
We did have a question from Fabio Ragusa on that airfoil that you had a moment ago with the round dent.
Yes.
He was wondering if you could measure the radius. How did it go? Where the blade meets the platform.
Right here, right there, I believe, is what we're talking about. That should be
Yeah,
an easy measurement for us.
Yeah, and he said it would be really interesting if you could find a defect on that radius.
This one looks pretty clean. Let's see if I have any others here.
Yeah, the 3-blade part might have some, Kramer, there.
Yeah, okay.
That would be maybe our most likely to be damaged there.
Okay.
If not, as you move on, I can go try and see if we have one that would have something like that. But measuring defects in radius corners like that is one of the primary applications of the tool in aviation, and not generally a problem. So
Yeah, it's
we'll
something
see
we
if
do.
we can find a part that is appropriate here.
Yeah, something we do often, and it's pretty routine for the inspec. These are all looking pretty clean on my desk here. Let's see if this one behind me has one.
All right. Hey Kramer, how about I'll go and try and find one real
Okay.
quick.
Yeah, I'll keep moving.
Maybe explain the various ways to output the data really quick before moving on, so people
Yeah.
understand reporting and CAD export and things like that. And I'll see what I can find.
Okay, perfect. So to do some output data to move your measurements out of the software itself, there's a few options. So if you want to move this measurement to export it, you can save it with this save icon, this floppy disk. And you have a few options to save it. So I can save it as a 4D file. That's obviously for the 4D software. That allows you to save it off, put it back into our software. You can go back through old measurements and recalculate with different cropping, with different shape removal that you've seen me do, different settings. And by saving it as a 4D file, it's just like scrolling through your this stack right here. You can put it back into the 4D software, reanalyze it in different ways later after you've taken the measurements. You could send it to me, and if you want help on any measurements, and I can analyze it for you, take you through it step by step on how I would do it. You can really save that for later and put it back in the software, use it, reanalyze it. It's a pretty useful tool, and we're always happy to help out if you ever have any questions on how you would analyze something. And we have other options as well. We have OPD files, CSV point clouds, and XYZ point clouds. If you want to export this data out to a third-party software, we can do CAD comparison. We can take our measurements, compare it to a CAD model you have, see where it deviates, see how much it deviates from what you would consider perfect. I think that would be a pretty useful application in the future. But there's just some options on how to save different measurements. All right, so in the meantime, I will go ahead and move on to a blade edge measurements, and we'll circle back around to hopefully we'll find a good defect in here somewhere on another part. We have a bunch of aviation parts sitting around the factory. So go ahead and take a blade edge measurements. There's a few different focus aids that we have. This one is more universal, and I think we might have a defect in Okay, I think we might have a defect on a radius here real quick that we can take a look at. So we'll set down the blade edge measurement. Come back to that in a second. I'll go back to the radius measurements. Look at a defect on this blade. Looks like we have one about right here. Go and take a look at that. Yeah, we have a few there. Okay, perfect. So we have some, looks like we have some defects right here. I'll go ahead and take a measurement like I have been. Let's put this up to it. Get the LED reflecting off my area of interest. When I'm ready, when I'm in focus, I'll click this button like that and take a measurement. Connect my live video. All right.
And then after this, Kramer, we'll have to, we want to show these folks edge break and radius.
Yeah, we'll get onto that. All right. So go ahead and crop down into this area that I want to see. I like this defect right here. I'll crop down on my area of interest. I'll look at this. I'll go like this, actually. I can go into traces here, move my cursor around. Like so. And I can just see how far this drops. So if I want to see a depth here, I can see maybe it's 47 microns right there. I could search around for a deeper point like that. But
and then
you get your
really
three.
the cylinder, right? And just use the feature analysis again.
Yeah, we can try that. So that we can use a tilt and cylinder right here. Try to move that shape. Okay, that looks good. Then we use feature analysis right there. And all right, there we go. So that's a nice, easy way to get this measurement in this tight radius right there on this blade right here. So we're looking right in there. You can see that little mark. I guess you can't really see that well on this camera, but it was right along this edge. But that's a real easy way to you just take the measurements, come back to it, get your area of interest, crop it down, remove that shape, and the feature analysis does the rest for you. So it's a pretty simple way to.
Thanks.
Yeah, that's great. All right, so we can keep moving along. We'll look at some edge break. Let's keep moving forward. Make sure we touch on everything. So I'll look at my edge break standard here. This is a standard that we had made specifically for our testing this application. And on this side, we have a chamfer. This side, we have a radius, and we have internal radii. In between, I'll go ahead and show you a closer picture right here. It's a good example. So you can see on this side, we have a chamfer, which is just a machined flat on a sharp corner, just to get rid of that sharp edge. On this side, we have a rounded edge where the edge is rounded off to remove that sharp edge. So there's a couple different ways to do edge break. And these are the two main ones right here. So on this side, you can see I'm taking a measurement on the chamfer. I'm perpendicular to this chamfer face. You can see the inspec at a 45-degree angle, perpendicular to this 45-degree chamfer. And I'm getting the LED reflecting off this left side, this right side, and that chamfer face. So I'm getting data on all three planes. In our edge break analysis takes the calculation from there. So I'll go and take a measurement just like that shows on this edge break standard. I'll do that chamfer first. And just similar to how I've been doing it the entire time, just putting it down, clicking a measurement when I'm in focus. I'm getting at a 45-degree angle here so I can be perpendicular to that chamfer face and get data on all three chamfer faces, chamfer planes there. Go back to my live video. the appropriate shape removal. Now I'll get this in focus. Once I'm in focus like that, I'll go ahead and take a measurement like so. All right, that looks good. I'll put in my chamfer analysis. What we'll do, we'll identify the pixels or the data points that belong to this left plane, identify the data points that belong to the right plane, and identify the data points that belong to the chamfer face. You can see that's what this is doing right here. The blue data points, it's identifying as this left plane, the red ones, this right plane, and the pink ones, this chamfer face. And it's giving you all of these chamfer results. And I can show you probably more simply in this diagram what each of those means. So this software is identifying this plane and reconstructing the material that's been removed during the edge break process, finding where these two planes intersect. It's giving that right length, which is a common call out on a lot of edge break drawings. So it's giving that right length, that left length of the material that is no longer there. It's obviously giving that chamfer length, the distance the chamfer is from the side to this side, and giving different angles in between in the center length. So it's reconstructing the material that's been removed, remove any tilt that you may have had to the part itself. So I didn't even really try to align it that well. I'm not perfectly vertical or anything like that. I don't have to be. I can be 45 degrees off if I want it to be and still get a good chamfer result. And so the 3D data is able to remove all that tilt and get this accurate chamfer result and display them nicely here. If I wanted to, I can set pass-fail criteria. So just for example, I can set this as my minimum and maximum, and you can see this would show up as green as passing. I could do, oops, I can set it to fail if I wanted to. Like that, it would show up as failing. So easy pass-fail, go, no go, chamfer results right there. And it's very quick, easiest way to do a chamfer measurement. And with stylus, you can, or any kind of 2D measurements, you're subject to any alignment errors. So you can see in the traces here, if I were to not get this chamfer perfectly perpendicular, you're gonna start measuring this artificially high at 1500 millimeters, or sorry, almost 1600 microns there, which we know it's 1440. So if you're not perfectly perpendicular, you're subject to alignment errors. Where with the 3D data, that's impossible. So I can do a rounded edge real quick. I'll flip this around, do this other side here. Just do the same way I was doing the chamfer, line it up like that, get all three, get both the planes and the rounded edge in there. Click that button when I'm ready. Go back to my live video. I'll get this in focus. There we go. Take a measurement. All right, put that in my rounded edge analysis. And it's gonna do the same thing. It's gonna identify this left plane, this right plane, and where that area of curvature begins. You see that's what it's doing here. These blue data points are the left plane, red data points are the right plane, and find that best fit curve for the curved area, removing any tilt with that 3D data that it finds. So alignment is not an issue, and giving you your edge break radius right here. And then I can show you a diagram of what each one of these parameters means. So here's your area of curvature and your edge break radius at that best fit circle. That right length is again, the intersection, and left length as well. And here are your different edge break angles that are on some callouts. So very easy, very quick, easiest way to get all of this data on this rounded edge.
And since parts have so many edge break callouts, that's amenable to robotic automation, right?
That is true. We can I'll go ahead and show you a quick video, real quick, just of a part that has a couple dozen edge break callouts. And we have this on a universal robot that is natively supported in our software, doing quick edge break analysis on each of these chamfers and rounded edges that are on this automotive part. So it's on a robot taking measurements on all of these chamfers right here. So because there are so many edge break callouts on a lot of drawings, automation is very key to speed up this process that can take days.
Yeah, I think that particular part had more than 50 features, right?
Yeah, that's true. I think it's 57.
So, and then we want to be
Okay, guys.
respectful of time, so maybe we
All right,
show
yeah.
you guys a true cylinder radius measurement and see what else questions and what else they might like to see.
Yeah, I'll quickly just do a cylinder measurements. I'll just do the microscope stand here. It's a cylinder, and take a measurement of that real fast. And we can get the questions and any requests. So I will take a measurement of the cylinder, like so. So I'm in focus here. Took a measurement. Measurement looks good like that. I'm a little overexposed. I can take a little better one. Let's go ahead and do that. Wait for the. All right. Oops. There we go. Okay. Okay, that's better. Sometimes if you're overexposed, you can lose some data. So you want to make sure there's no red pixels in your measurements. So I'll put this into the 3D radius of curvature. Put my cylinder into this edge break analysis, which is the 3D ROC, and then get my radius curvature result right here. So just like these two, it's removing any tilt I had with the inspect, because I wasn't perfectly orthogonal to this microscope stand cylinder. But it doesn't matter, it can remove that tilt. And I mean, you can see I was off. This side was closer to the inspect than this side was, but the 3D data removes that, gives the software the ability to remove that tilt and give you an accurate radius of curvature result right here within seconds of taking the measurement. So easy to do, very quick, that saves you time.
Great. I have a quick question from the audience about really stitching. Is it possible to merge together multiple fields of view to have a complete scan of a surface or a geometric tolerance? And of course, with the aid of a robotic arm or CMM.
Yeah, so I can answer that. So we do have some prototype stitching code currently for when you have features that span multiple fields of view, so that there's a good way for the system to know how the two fields of view were aligned. If you have something that's substantially featureless, for instance, this cylinder, there's really no good way to know from measurement to measurement without robotics where it is. So we're not able to do that. But stitching is on our 2021 roadmap, both using the coordinates as given to us by the Robotic Automation, and then also again looking for, say, scratches or large corrosion areas that span multiple fields of view. So right now it's just in engineering phase within 4D, and but we are looking at that. One thing we typically, unless you absolutely have to stitch, we don't recommend it. Every field of view has more than 4 million data points here. So this really isn't a system, say, for CAD comparison of shape, just because the data density is so high. And if you stitch together a lot of measurements with 4 megapixels per measurement, you pretty rapidly run out of memory. So for automation, most of our customers are content making sure they have 100% coverage rather than stitching. But it is something we want to allow for limited cases. So again, it's on our roadmap. All right. I think we're pretty well done, right, Kramer? So we can open it up for further questions, or if people have additional samples they would like measured, we'd be happy to entertain that. We can go over time if people want to stay on the line as well.
Excellent. So we do have a question. We would like to verify an acetabular cup printed by 3D printing. The material of the cup is, it looks like it's titanium, and this cup is covered by a lattice structured by a bulk solid base. We would like to verify if there are some cracks below the lattice structure. Is it possible with this technology?
So we can only measure, being an optical technique, things that are visible to the instrument. So we can't do subsurface measurements, but if there are cracks that extend to the surface, we can certainly measure their width and length typically, depending on how deep they go and whether we can get light in and out of the bottom of the crack would determine whether or not we can measure the depth. But we do have people that look at welds, and so they'll do crack measurements of welds. But again, not subsurface. They have to actually be a surface crack. And one thing, as you see, the inspect measurements are very fast. And so if you would want to send a sample in, we could very readily, set up a web demo right now, since travel is not really possible in most parts of the world, and show you the measurement result very quickly and verify or not whether that's useful output for you. So if we don't have any other questions, we are just about out of time here. I did want to, let's see, pull up our contact info. Kramer, if you could, here, I can do that.
Yeah, I can go ahead and, yep, all right.
So, trying to, can you see my screen?
Yep, I can.
All right. So if folks have questions, you can go to our website. It has a variety of both training and kind of application-based videos. Please feel free to email Kramer or myself here at 4D Technology, which is a subsidiary of Onto Innovation. Or again, you have just excellent local representatives. Gwendol handling France, Spain, and the Benelux territories, and Alessandro in Italy. Both are very well versed in the product and can certainly help you out. So with that, I thank you all for your time this afternoon, and good luck to you all. And if you have any other measurement questions as well, we're happy to entertain those, not just on this product, but on things like roughness measurement and other critical surface metrology. So thank you again.